So we have the two wires here. One of them has a current, and we're showing the magnetic field around the wire. And if another wire is close by, that magnetic field of the first wire begins to affect the current charges flowing in the second wire. Now it's not shown here, but the same happens with the second wire. It's going to have magnetic field lines that are going to then react to the charges in the wire number 1 here. So you have two things going on. Now it turns out that when the currents are going in the same direction, the forces are attractive. And when the currents are going in the opposite directions, the forces are repulsive. You'll have to ask me or remind me to tell you about the time I did an experiment. I wasn't planning to, but I actually proved this. It was kind of a crazy situation, but ask me, I'll tell you. So let's start with the force equation, and we had that the force vector is equal to the current times the length vector cross product B field. And this, if we had this as just a value, that was equal to I L B sine of theta. But in this case, the sine is always going to be 90 because the current and the magnetic field are always going to be perpendicular. So this will be F max. So our F max is going to be current times length times magnetic field. So let's do some playing here. So we know that our magnetic field for wire 2 is going to be equal to mu naught I in wire 2, current in wire 2, divided by 2 pi times the distance, d. And if I put this into our force equation, my force on wire 1 is going to be equal to the I1 times B2, my magnetic field due to wire 2, that's going to be current 1, and times the length that wire 1 and wire 2 are together, so we have length 1. And if we put in our B2, we get force on wire 1 is equal to mu naught I1 I2 over 2 pi times the distance between the wires, and then we're going to multiply that times the length L1. Now I can do the same thing for the other wire. I can say that my magnetic field due to wire 1 is going to be equal to mu naught I1 over 2 pi d. So F2 is going to be equal to I2 B1 times L2, length that the magnetic field is on wire 2, and that's going to then simplify this to mu naught I1 I2 over 2 pi d L2. Now usually L1 and L2 are the same, and so usually F1 is equal to F2, which makes sense because there would have to be some kind of equalizing of forces to to keep things static if necessary.